lesson, we want to talk about radioactivity. And so what I want to do is to give you the basic concepts that will enable you to be able to calculate the mathematical concept of radioactivity. So there are some concepts which most of the students or those people who are trying to understand radioactivity leaves behind. And so these are the concepts we are going to talk about. So first, we will start with the stability of an isotope. Now remember, radioactivity deals with nuclear reactions, only nuclear reactions. There's nothing more. So here we don't talk about chemical reactions, but nuclear reactions. So stability of an isotope is our first concept. So you need first to understand what is an isotope. Once you understand what is an isotope, it becomes very easy to understand radioactivity. So isotopes are atoms of the same element with the same atomic number. Mark that. They have the same atomic number but a different mass number. So it is also somebody else can say that an isotope is an atom. These are atoms of the same element with the same number of protons but different number of neutrons. Actually, when the neutrons are different, this is what makes the mass number different. Remember, mass number equal to number of protons plus neutrons, the sum. Remember that. So it is important to understand what is an isotope. So a nuclide is an atom with a defined mass number, atomic number, and atomic number. So a nuclide is actually an isotope. So a nuclide and isotope are the same thing. So I have one isotope I have given here. Chlorine is an isotope because we have chlorine 37 and a chlorine 35. Look at this one. This chlorine, the mass number here, you can see it is 37 and this one is 35. So they have different mass number, but look at the atomic number. 17, right? So this is what we call an isotope, a nuclide. They have the same atomic number but a different mass number. Another important thing you need to understand, this 17 that is below, we call it a subscript. A subscript, and the 35, which is the mass number, is the superscript. So the number which is above here, this number here, represents the mass number. The number that is below, which we call the subscript, represents the atomic number. So when somebody asks you, what is the atomic number of this element or this atom, you will say it is 17. What is that is the atomic number. The mass number is 35. What about this one? Atomic number is 17. Mass number is 37. Very important. Another thing we want you to understand is the stability of a nuclide. A nuclide or an isotope can be stable or unstable. So we want to see a nuclide, an isotope which is unstable. What makes it unstable and what makes it stable? A nuclide is said to be stable if its neutron-proton ratio is equal to 1. So if the number of neutrons divided by protons, the answer is 1, that nuclide is very, very stable. It will not disintegrate. But any nuclide, nuclide or isotope whose ratio is not equal to 1, is less than 1 or more than 1, will always disintegrate, will always undergo radioactivity, will decay spontaneously to ensure that it has the stability of 1. Stability of what? Of 1. Very important to note. So from there, you can be asked to state the factors that makes a nuclide stable. So we talk about that. We'll try to attain the stability of 1 by undergoing radioactivity. So radioactivity takes place in the nucleus of an atom, unlike chemical reactions that takes place in the energy levels involving electrons. So a quick example, an example of stability. Now look at oxygen. As oxygen here, you can see this one has can increase this one to 20. This oxygen, you can see the atomic number is 8, the mass number is 16. Atomic number is 8, mass number is 8. It means it has 8 neutrons and 8 protons, so that the sum is 8 plus 8, which is equal to 16. So it means that this oxygen is very stable, because 8 divided by 8, number of neutrons divided by 8 protons, the answer is equal to 1, and that one tells you that this atom or this nuclide is very stable. That's stable and did not undergo decay. It doesn't decay. It does not decay. Chlorine. Look at chlorine. 37. So atomic 17, and then that mass number is 10. That means it has 18 neutrons and 17 protons. That's correct. Therefore, neutrons divided by protons is 1 to 0.30. It means that isotope is unstable and therefore will decay, trying to attain the stability of what? Of 1. Will always decay. So that's how you will know a nuclide which is stable or unstable by just simply calculating the ratio of neutrons divided by protons. If you get 1, that nuclide is stable. Now, what is radioactivity then? Radioactivity is the spontaneous disintegration or decay of an unstable nuclide, forming a stable nuclide of a different element with an emission of particles and energy. You can also say that radioactivity is the process where an unstable nuclide breaks up to produce another nuclide of different composition with an emission of particles and energy. Now, spontaneous here means that it does not need any energy to start. If an isotope is unstable, will just start naturally, spontaneously. So it will just disintegrate or decay. Isotopes which are radioactive are called radioisotopes. So what are radioisotopes? These are unstable isotopes. Unstable isotopes which are likely to undergo radioactivity are called radioisotopes because they are radioactive. A radioactive substance is a substance which is unstable and likely to undergo radioactivity anytime. The spontaneous disintegration of a radioactive nuclide is called radioactive decay. Radioactivity is a nuclear process and is not a chemical reaction. So quickly, you should know the differences between a chemical and a nuclear reaction. So nuclear reaction, you can see the differences. It is not important for now. Another important thing, you should know two differences of, we have two differences. We have natural radioactivity and artificial. So it is important you should know that. Another thing that is very, very critical in this radioactivity topic is the particles that are emitted during disintegration. So here, all unstable nuclides naturally undergo radioactivity, trying to attain nuclear stability with the production of the following particles or radiations. So when they are undergoing radioactivity, they give out radiations, and the first radiation is the alpha particle or alpha decay. This is the alpha decay. Now this alpha decay, the most important thing is to know the characteristics of an alpha decay, and I have given all the characteristics here. There are around 6 of them. So once we know those characteristics, then calculating will be very, very easy. Calculating will be very easy. The alpha particle, number 1, alpha particle is positively charged like protons. Very important. So it is important to know that an alpha particle is positively charged. Very important. Because now when we are going to, this alpha particle is going to be put on an electric field. So if you don't know that it is positively charged, you will not know to which direction it will be deflected. So it is important for you to understand that alpha particles, they are positively charged. Very important. Positively charged. Alpha particle has a mass number of 4 and atomic number 2, therefore equal to a charged helium atom. So they have a mass number of 4, atomic number of 2. That one is also important. What about the penetrating power? Alpha particle has a very low penetrating power. Very low penetrating power. So, and thus can be stopped or blocked or shielded by a thin sheet of paper. A piece of paper can block alpha particle. So it will not penetrate through a piece of paper. Therefore, it has a very low penetrating power. Number 4, alpha particle has a very high ionizing power. Very high ionizing power. Ionizing power. Thus causes a lot of damage to living cells. Causes a lot of damage to living cells. Even when you go for X-ray, they don't use alpha particle rays or radiations. Actually, they use gamma. They use gamma because they have very, very low ionizing power. Gamma has a very low ionizing power, as we shall see later. Very important to note that alpha particle has a very high ionizing power, thus cause a lot of damage to living cells. A nuclide undergoing alpha particle. Now, this is what is very critical, that a nuclide undergoing alpha decay, it has its mass number reduced. Yes, reduced by 4, and its atomic number reduced by 2. Very important. Now you see the reason why you need to understand the atomic number and the mass number. When you are given an isotope, you should know that the number that is above is on top is the mass number. The one that is below is the atomic number. Very important. If you don't understand that, then you will not be able to manage. You will not manage these things. So always read twice, thrice this Roman 5. A nuclide undergoing alpha decay has its mass number reduced by 4 and its atomic number reduced by 2. We will do examples and you will see. The last characteristics we are talking about is that they are diffracted. So alpha particles are diffracted by both electric and magnetic field. Yes. So in an electric field, they are diffracted towards the negative. Very important. Because they are positively charged. Now, once you know that they are positively charged, you will be able to know that alpha particle, they are positively charged, and in any case they are put on an electric field, they will be diffracted towards the negative. So that's why it is important. So let us look at this diagram here. Now this is a radioactive source which is giving the 3 radiations, gamma, alpha, and beta. So the one that is positively charged is alpha, right? The green one. So it will deflect towards the negative because this one is positively charged. So if it is positively charged, it will be deflected towards the negative. So that is important for you to note. So there are some examples for alpha decay. I want just to do one example for you so that you can see what we are saying. Actually, this one we call it a nuclear equation. A nuclear reaction. That this is now a nuclear equation. This one is a nuclear equation. So as you can see, lead, the atomic number is 84 and the mass number is 210. So after undergoing alpha decay, the mass number is X and the atomic number is 82. So what has happened? Because it is alpha, we said for alpha, a nuclide undergoing alpha decay, as we said, has its mass number reduced by 4 and atomic number reduced by 2. Now look at this equation. So the mass number we don't know, but the atomic number we can see it has reduced by 2. So 84 minus 2, 84 minus 2, it is 82. So what do you expect the mass number to do? So therefore 210 minus 4, here we will have 206, and that is now the answer we have here. That is 200, and you can see here now the mass number is 206 because during the decay, the mass number will decrease by 4 and the atomic number will decrease by 2. And then you put this alpha, here. You need to put it like this, so that now when we want to go back, if we want to go back to reverse, what you do, you add. So take 2 here, this 2 here, add to 82. What do you get? 84. Take this 4 here. Are you seeing this 4 here in the helium? Add to 206. What do you get? 210. So when we go this to the left, we add. When we go to the right, we subtract. So these are the examples. I hope you write them down and you will practice on them. I have several of them. These are others. So you will write them and you will use them as much as you want. Let me go to the next one. The beta particle. Beta particle. The beta particle has the following main characteristics, which are very critical. Property number 1, or characteristics number 1, is that beta particles are negatively charged. Negatively charged. Very important. So if they are negatively charged, when we have a radiation source, when we have a source of radiation, radioactive source, we know that the alpha particles are negatively charged, and this has a positive and a negative and a positive, as you can see. Therefore, beta being negatively charged, it will be deflected towards the positive. Remember, like charges attract and like repel. So therefore, the beta particles, as you can see, this one will be deflected towards the positive, because themselves they are negatively charged. Negatively charged. Very good. So that's property number 1. Number 2, Roman 2, is that beta particle has no mass number and atomic number of negative. So they don't have mass number. Very important. They don't have a mass number, but they have an atomic number of -1. Therefore, they are equal to a fast moving electron. Equal to a fast moving what? Electron. So when we are writing this one, we put it like this. We put E, which stands for an electron, then the mass number is 0 and the atomic number is -1. So that is for a beta particle. Beta particle has a strong penetrating power. Important to note. They have stronger penetrating power than alpha particle. You cannot compare with alpha because they are more powerful in terms of penetration. Thus, can be stopped or blocked by a thin sheet of aluminum foil. So, beta particle can only be blocked or stopped by aluminum foil. It means it will go through a piece of paper. Yes. And number 5 or 4, beta particle have a less ionizing power, less using power to cells than the alpha particle. Therefore, beta will not damage the cells like alpha. So they have less ionizing power. Very important. A nuclide undergoing a beta decay has its mass number remain the same, and particle we are saying that a nuclide undergoing beta decay has its mass number remain the same, and its atomic number increase by 1. Very important. So during the decay, and if the decay is a beta particle, the mass number will not change because it is 0. We have said that. But the atomic number will increase by 1. Not reduce. Remember that. Increase by what? By 1. Very important. Lastly, they are deflected both by electric and magnetic fields. In the electric field, they are deflected towards the positive because they are negatively done what? They are negatively charged. Therefore, they will be deflected towards the positive because they are negatively charged. So that's why I'm telling you that these characteristics are very important. So in terms of penetration, we have said that I have 3 lines here. We have radioactive nuclide radiation source. This is the black thing, here is the source. So we have blue, which is the alpha rays. Alpha will be blocked by just a piece of paper. This one is a piece of paper. Because beta, they have more penetrating power than that of alpha, therefore will penetrate the piece of paper and be blocked by a piece of aluminum foil. The last one is the gamma, which has very, very high penetrating power. They will penetrate through the sheet, through the aluminum foil, and then blocked by a thick lead block. It is the thick lead which will block it. So this is gamma. Very good. So let us look at an example of alpha decay, not alpha, a beta decay. So we have sodium here, which has atomic number of X and a mass number of 23. So what happens? What have you seen? What has happened? So because it is undergoing 1 beta decay, the mass number is going to increase by 1, and the atomic number is going to increase by 1, and the mass number remains the same, as you can see here. So if it has increased, we can see here from here, this is 12, this is 23. So what could be the original? If this is 12, it means this one should be 11. Let us look at this one, number 2. Let's look at this number 2 here. Thorium has atomic number of X, mass number of 234. So it is forming a Pa of atomic number 91 and the mass number of Y. So here Y should be what? Should be the same because alpha beta, the mass number is 0. Therefore, Y is 234. What about this is 91. It has increased by 1. Therefore, the original must be 90. So the original is 90. So there are several examples. So you can go through them. And whenever you have a problem, I'm always available on phone. You can text and I can explain for you. Lastly, we want to talk about gamma particle. Gamma particle are neither positively or negatively charged. Therefore, they are neutral. Very important. They have no mass number nor atomic number. They are equal to an electromagnetic wave. So they don't have any atomic mass, they don't have mass number. Gamma has very, very high penetrating power and thus can be stopped by a block of lead. Very high penetrating power. But they have a very, like I was saying, that the gamma particles have very low ionizing power, thus causes less damage to living cells. A nuclide undergoing Y, we use this sign here. I don't know whether you can call it Y, but decay, this is gamma decay, has its mass number and its atomic number remain the same. Nothing changes. They are not diffracted by either electric or magnetic field. Since they are not charged, they cannot be diffracted. So everything remains the same. This is an example of alpha of a gamma decay. Very important. Therefore, now we can comfortably look at this diagram. And this one that is I have given the green is the gamma rays, because they penetrate piece of paper and aluminium, high penetrating power but very low ionizing power. The red one is a beta particle which penetrated to a piece of paper and be blocked by aluminium, and then the blue one is the alpha rays, which is blocked by a piece of paper. In terms of diffraction on an electric field, now you can comfortably say that this one with orange, we start orange or what, whichever color it is, this one is the gamma, because it is not diffracted to the negative or the positive because it has no charge. So the one that is in the middle straight line is actually the gamma. The alpha will be diffracted towards the negative because they are positively charged. And then finally, the beta ray or particle will be diffracted towards the positive because they are negatively charged. Another very important one thing I want you to know is that the beta particle are very light. That look at the diffraction here, the size from here up to here, and then look at this size from here up to here. So the diffraction, because this one is very heavy, alpha particle is very heavy, therefore diffracts very diffracts at a slow pace or what. Look at this one. It deflects most. It deflects most because it is lighter than alpha. So let me take you through this graph. I have a graph here which is remaining amount, time, which is time here. So we start with 400 and then look at this. The half is 200, another half is 100, and another half is 50. So we are going a half down the graph. Now I want you to find the time taken for this 400 to decay to the half its original mass. 400, the half of 400 is 200. So look at from 0 to 8.5. This is number in days, time in days. So it will take 8.1 days to decay to a half of the 400, which is 200. Now let us see, a half of 200 is 100. So go across 100, come down. You find it will take 16.2 days to decay up to 100. But now the difference between 8.1 and 16, you find that it is 8.1. So across as you move, you will find the constant number of 8.1. It will take 8.1 days for this nuclide to decay to have its original mass. So it will take, for 50 to decay to 25, it will take 8.1 days. From the graph, it can be seen that after every 8.1 days, the amount of the substance remaining is half the previous amount. From the graph also, it is observed that the remaining amount never reduces to 0. The time taken for the mass to reduce to a half the previous value is a constant, 8.1 days. Very correct, very important. This constant value is called a half-life. So the reason why I want you to do this is to know a half-life. What is a half-life? The time taken for this mass to decay from 400 to 200 is what is called a half-life. The time taken for 200 to decay to 100 is another half-life. From 100 to 50 is another half-life. From 50 to 25, which is a half, is another half-life. So you should know it is a constant, and it is, for this case, it is 8.1. This constant is called a half-life. Therefore, you need now to know what is a half-life. Read, repeat, and understand what is a half-life. So a half-life is the time taken for a radioactive nuclide to spontaneously decay to have its original mass. Please make sure you repeat severally and understand that. What is a half-life? The time taken for a nuclide, a radioactive nuclide, to decay to a half its original mass, a half. So look at this, from 400 to 200, that's one half-life. From 200 to 100, that's another half-life. From 100 to 50, that's another half-life. So here, from 400 to 550, I will count how many half-lives. 1, 2, 3. We'll have 3 half-lives, right? But a single half-life is the time taken for a nuclide to decay to have its original mass. Having done that, now I think we are ready to go to the questions and do the questions.